So let's introduce the concept of angular momentum in the screencast. And just like linear momentum being an extension of F equals ma, or Newton's second law, angular momentum is an extension of linear momentum. So buried in this is still our concept of Newton's second law. And so the way that we state this is with a lowercase h, and it's a vector, and we say that this is the angular momentum of mass p with respect to point O. And here point O is an inertially fixed point, so this is important to keep in mind in this screencast. And it's defined as the position vector p with respect to O cross with the linear momentum of p with respect to O. Another important feature of angular momentum is that when we define the angular momentum, we need to reference it to a particular reference frame. So the reason why that is because inside the expression we have the linear momentum, which is observed in an inertial reference frame. And recall that the linear momentum is observed in a particular reference frame because the velocity, which linear momentum is mass times velocity, velocity is observed in a reference frame itself. So always be sure that you denote what reference frame you're making the observation of the angular momentum within. The units of angular momentum are a little bit strange. They're actually kilogram meters squared per second. And we get this because what we have here is a length in meters, and then we have the linear momentum, which is in Newton seconds. So another way to write this is that this is equivalent to Newton second meters. One last thing to point out is the direction of angular momentum. Angular momentum is a vector, so that means it has both a magnitude and a direction. And it's made up of a cross product in which we have a planar position vector and then a planar linear momentum. And so because it's planar, let's say that we're expressing all of our terms within an inertial basis, E1, E2, and E3. Then that means that our position vector of p with respect to O is going to be expressed in only E1 and E2 terms for it to be in the plane that we're dealing with, because E3 is sticking out of the plane. And also our linear momentum vector is also going to be expressed in the E1 and E2 basis. And so when we take the cross product of something that's expressed in the E1, E2 basis with something crossed in the E1 and E2 basis, the only result that can come from that is a vector that's pointing in the E3 direction. So in planar problems, the direction of the angular momentum is either going to be out of the page or into the page, depending on whether your answer is negative or positive relative to the E3 vector and how that's defined. Now let's get some practice calculating the angular momentum with respect to a couple of points, and we'll do that using our simple pendulum model. First, let's find the angular momentum of P with respect to point O, and then we'll find the angular momentum of point P with respect to Q, and we'll do this observed completely in the inertial reference frame. So when we look at our pendulum model, and we're going to find the angular momentum of the mass at point P with respect to point O, O being an inertially fixed point at which the pendulum is rotating around. Let's write out our expression for the angular momentum of P with respect to O. And for this we have that the angular momentum of P with respect to O is the r of P with respect to O, the position vector, crossed with the mass of P multiplied times the velocity of P with respect to O as observed in the inertial reference frame. So let's take each of these components and calculate them individually. We have the position vector of P with respect to O. We see that this is the length L in the ER direction. And we take the time derivative of this expression as observed in the inertial reference frame to get the velocity of P with respect to O. And it's equal to L theta dot in the E theta direction. So put all this into our expression. And then when we take the cross product of these two terms, we get an expression where you have the mass multiplied times L squared theta dot. And then it's the cross product of ER and E theta. So that's going to be in the positive EZ direction. Let's do a double check on our units. So we have kilograms, we have meters squared, and then we have theta dot, which is in radians per second. So that satisfies our kilogram meters squared per second. So next, let's take a look at the angular momentum of P with respect to point Q. Now point Q is an inertially fixed point as well, but point Q is located the distance d to the left or in the negative e2 direction from point O. So first write the generic expression for the angular momentum of P with respect to point Q. And you can see that all we've done here is that instead of referencing point O, like we did in this expression, we're referencing point Q. And so write out the position vector and the velocity vector, where the position vector r of P with respect to Q is going to be the distance d in the E2 direction, and then we're going to add to that plus L in the ER direction. For our velocity term, we're going to take the time derivative as observed in the inertial reference frame for each of these terms. So for the first one, our E2 vector is in the inertial basis, so it's going to be the time derivative of the scalar d. Because these 2 points are inertially fixed, the time derivative of d is equal to 0. So there is no time derivative, it's equal to 0 for the first expression, and for the second, it's the same thing that we have here. The time derivative as observed in the inertial reference frame for L in the ER direction is L theta dot E theta. We substitute these into our generic expression, and now after doing that we see that we have to take a cross product between these 2 expressions, but our first expression is expressed in a mixed basis because we have an E2 vector and we have an ER vector, both of those that we're going to cross with an E theta vector. We know that ER cross E theta is EZ, but we don't know right offhand what E2 cross with E theta is. So let's convert our E2 into the polar basis and express it in terms of ER and E theta. And E2 is equal to sine theta ER plus cosine theta E theta. And then we plug this in to get the following expression. And then when we calculate the cross product, we have an ER cross with E theta, which will give us an expression or a quantity in the EZ direction. And then we have E theta cross with E theta, which any vector cross with itself is going to be 0. And so then our final expression is the mass at point P multiplied times L squared theta dot, then all that quantity multiplied times what's in this parentheses, which is 1 plus d over L sine theta. And so you should notice that the magnitudes of these angular momenta are different from each other, and they change based on the point with which we're taking them to. So the angular momentum of P with respect to O is mp L squared theta dot, and then the angular momentum of P with respect to Q, we see that wrapped up in here is the angular momentum with respect to point O, but then it's scaled by this factor of 1 plus d over L sine theta. And the reason for this is that when we're taking the angular momentum about this fixed point and comparing it to the angular momentum about this fixed point Q, is that we need to consider what the change in the moment arm is that we're using. Because the moment arm from O to P is the distance L, and it's along the pendulum. But the moment arm from Q to P is a longer moment arm, so we would expect that this r cross linear momentum is going to be a larger quantity. And in fact, another expression for this when we're using inertially fixed points is called the moment of momentum, because it has a moment arm crossed with the linear momentum. And so as you're working these problems, I encourage you to use the intuition that you developed in statics with an r cross f, where you saw that the longer moment arm created a larger moment. In this case, think of it as the moment arm from an inertially fixed point to the mass that we're considering for the angular momentum, and the angular momentum should be larger for a longer moment arm.